5, 4, 3, 2, 1. Silence. Good morning, good morning, good morning, good afternoon, good evening, wherever you are in the world. We are the Saturday Science Science Chats, and every time I start out talking, because it's earlier in the morning here, I get a frog in my throat, but you don't want to miss it today. We're going to be talking about quantum mechanics, and we'll be talking with Eric Reiter in a little bit. Yes, sir. I am David D. Hilster from the John Chappell Natural Philosophy Society and, of course, Dissident Science. And this is, you have tuned in to our Saturday Science Chats. And today, of course, we are going to be talking about quantum mechanics going wrong. And we have a great person with us today, great scientist and experimentalist, Eric Reiter, and he's going to be talking about his model and his criticisms of the quantum mechanics. But of course, before we go, we'll be do some announcements and introductions and who we are, etc. And again, I want to thank everybody watching because it's very important, because without everybody watching, we don't have our audience, without our support, and it's greatly appreciated. Let people know about this channel. It's really the only one out there on the entire internet that does this. That is, we look at people who are serious people, scientists, amateurs, professionals, engineers, you name it, who are working outside the mainstream, who are critical thinkers, And we support all of those people. And I want to thank you all for watching and supporting this. I know I get emails from around the world thanking us for putting this on. And so hats off to everybody who is here watching and participating. Very important. Of course, we are where critical thinkers meet. We are the John Chappell Natural Philosophy Society, named after John Chappell, who is I think he had a PhD, and I think from a decent college too. But he started a group called the Natural Philosophy Alliance in the early 1990s. I met up with him in 1996 and had been involved with that group of people around the world for now, oh my gosh, coming up on, over 20 years for sure, 25 years. And we are, of course, our mission statement is to be an organization that above all promotes critical thinking without malice, something that other places do not do and other groups that do not do, to be an organization that supports, publishes, promotes, and serious work outside mainstream science, to provide a forum for open debate about modern topics in physics, cosmology, philosophy, mathematics, and other things as well, to provide a forum for presenting serious papers and theories without fear of censorship, and to be run and controlled entirely by its membership. And that's many of you are watching today. We all appreciate your support, and our group is growing all the time here. Who we are? Well, we are open to challenging mainstream science. If you ask almost all of us, we have the same response. Mainstream science is in a mess. It's been lost for as long as a hundred years. 100 years, don't go too far. But that's what is in common with all of us. We allow and encourage competing ideas, which is very different too, because you're not supposed to have competing ideas. And then, of course, we follow the scientific method. I think people who are outside the mainstream, they just throw away the entire universe and make up their own rules. That's absolutely not true. In fact, the truth is that we know a lot more a lot of times about the rules that are out there because we look at them critically and find the problems. People in mainstream don't want to do that. They want to repeat what's been taught, don't question it, and if you do, you're ousted, it's not the way to do science ever. We also consider, like Aristotle says, an idea without accepting it. That is, today we have a person who's going to be talking, and to keep an open mind about everything you hear. So that's really, really important. And then also we give voice to the voiceless, that is, the people who aren't being given a platform. And of course, this is where science advances. It always has been outside the mainstream. For some dumb reason, we don't have universities that encourage people to think critically. Who we are not, so people you do know, we don't have a specific point of view. That is, we're not all etherists. We're not all anti-relativity. We're not all Big Bang. We're not all one way or the other. We have many points of view. There are a lot of commonalities now. During the last couple decades, we do have a lot of things we've all come to the same conclusions. Like, I'll give you an example. Energy isn't real. It's a great concept, but it's not real. There's a good example. We're not a general science organization. You're not going to see us doing videos on how baseballs fly through the air. So we are not a new age that is sort of like Zen, and we have science poetry. What somebody in our group has talked about, which is like science poetry. We don't talk about conspiracies or UFOs. We do know there's suppression of work in science. We do talk about that. But the reason we don't talk about all those things, including also religion, I got to put that up on there, is that we want to stick to foundational science like gravity fields, magnetism, tectonics, math, philosophy, Big Bang, cosmology, the whole thing, because there is so much to work on just at the fundamental level. We just aren't getting into how our organization will make your life better and the universe come to a wonderful Zen. We are interested in what is light, or how quantum mechanics really has a lot of problems, which we'll be looking at today. If you haven't visited our website, you should. Science Woke, which is really an online magazine for critical thinkers. You can find, we got a lot of people read that daily. And it's got great articles to introduce things like, oh, what's wrong with mainstream science? If you haven't really thought about that or what that could mean, you can go there, you can click on problems and find out the problems, and then see all the people and great scientists involved in trying to come up with better models. And you'll see our guest, Eric Reiter, he is in there. And sciencewoke.org. Our community is naturalphilosophy.org. We acquired that domain name. It was not real cheap, wasn't that expensive, but we feel like we are the best keepers for that, because natural philosophy is the term of what people use, like Newton was a natural philosopher. He was not a physicist, because at that time there was not a word for physicists or physics or I'm not even sure cosmologist was even used then. So we've used the word natural philosophy, trying to get back to the roots of science, physics, and cosmology. And we are a critical thinking community. You can sign up. It's free for anybody to sign up, and you can start joining in the conversations that they have there. Really great website. Also, we have a natural philosophy Wikipedia, where you can find over 10,000 pages of abstracts, works, topics, and books, and scientists. And if you are a scientist working outside the mainstream, you don't have your profile on there, you can, because they're not going to put my profile on Wikipedia, because Wikipedia is, of course, the consensus of the world's knowledge, and anybody who's outside that consensus is considered to be pseudoscience. So it isn't the collection of all the world's knowledge. It's a collection of a curated knowledge of what is acceptable to everything, everyone, including science. We do have memberships to our organization. Our monthly memberships range from $5 on up, and our annual membership from $35 on up as well. And we do accept donations, and that's how we survive. And the reason we are here today using StreamYard today, which is a service, those services cost money, and so do all our websites. A couple $1,000s a year with all of our websites and everything we do. So it's very important, and we do accept donations, and we want to thank all of our patrons. Dr. Cynthia Whitney, who is our chief research scientist for the group, got her degree from MIT in special relativity, and she applied it to ring gyroscopes, and it didn't work. And so she became a dissident. She figured, if I get a PhD from MIT in special relativity and it doesn't work on the first application, there's something wrong. And her professor said, yep, yeah, there is. We just don't talk about it. I can't believe that. Nick Percival is also, if you haven't checked it out, Nick of Time. Go to Nick of Time, Nick Percival. YouTube channel, great YouTube channel with a lot of things about time and relativity. You want to check that out. Duncan Shaw, who has contributed numerous times. He's an etherist. He's got great publications. You can look him up as well. And anonymous donor, I want to thank him and a couple other people, Bob DeHilster and Kurt Renshaw, for their contributions. We are currently accepting papers. We already have some papers being sent to us. You can send them to proceedings@naturalphilosophy.org. We will have the official launch page this month. I do promise to do that. We are finished. My dad and I are finishing. Well, we'll talk about that in a minute. To take place online in the fall. So you want to get part of that proceedings. And if you're in the proceedings, you're going to be presenting your paper. We're going to put that on our YouTube channel, and people will be able to watch it ahead of time. And then we're going to have a Zoom meeting, and everybody can talk about your paper and discuss it. So it's going to be actually a lot of fun. We had a meeting about that couple months ago online in this show, and we came up with a really great format, I think, of how to do this. So it'll be the fall of 2021 in the Northern Hemisphere. Yeah, I lived in Brazil 3 years, and the fall is a different time of the year than it is up here. So our CNPS are ready to publish. I know George Coyne will be publishing very soon his Notfinity book. And when he does, he'll be coming on and talking. We had him on before. I really like talking with him. He is an absolutely fascinating, amazing mind. One of those people, I think his mind goes faster than his mouth sometimes, but he is very, very, very a brilliant guy. And if you haven't checked it out, this will be his second edition coming out, and there's quite a lot of addition to it. So that'll be coming up. Keep your eyes open for that. Then there is an Ether book with over 400 pages. My dad has been helping edit that to a person whose name is his pen name. We just call him Ramsey. And then, of course, my dad and I, absolutely, this is our book, and it is being finished this weekend. I'm pretty sure it will be done. We're going to be sending it out to our list of readers, and then we will be publishing it soon. So we are doing lots of things coming out from our group. You want to check out the community news, where I bring up some things. And the reason I'm bringing up Jeff Yee is because he'll be coming on next week. If you haven't checked out his energy wave theory, it is absolutely amazing. It is amazing. It is an ether type theory, but he uses waves quite a bit, obviously from his the name. And if you haven't checked out his videos, he had a new one come out called Simulating Molecules. He's actually programming this stuff. His model, like our model and other models, newer models, is completely Newtonian. There's no magic going on there. So that's right. If you haven't checked out his model or his website or his YouTube channel, want to check it out, he did have this new video. So when we have news from our community, bring that. And we have play coming attractions. Yes, they are coming, and we get new people all the time. Yes, next week we're going to be having the energy wave model, computer modeling the quantum world. Man, I'll tell you, the penultimate video from Yee is absolutely amazing. And the guy putting together quarks in formation has the Newtonian kind of field. He doesn't. I don't know what he has for his field, but he does do it. He uses charge, I guess, and it orbits in the SPDF orbitals for an atom. It is. I haven't checked it out. Check it out, and you can actually download it and play with the model. Atoms. You can make isotopes and all kinds of stuff. And he's got. It is absolutely amazing. And I told him, I said, you got to come on, and he agreed to do that. So you want to check him out. And of course, we have coming up finite theory, Phil Borkert. Got to talk with Nick Percival. He's been curating this talk, so want to get that one up, coming up soon. Of course, disruptive. He's going to be coming up as well, hopefully this month as well. But of course, we're always open, and you can be on our Saturday morning show. And we'd love to have you if you are working on some serious work and think other people should know about it. And of course, you're not getting invited to universities to talk about how Einstein is wrong, or how the Big Bang is wrong, or how quantum mechanics is wrong, or how particle physics is wrong, etc., which probably isn't happening. So it can be you, of course. To play today's bumper. Yes, today we're going to be talking about quantum mechanics and how it's wrong with Eric Reiter. I'm going to say Reiter. If you don't know about who Eric is, he does have a website. I'll put that up here, actually. I can do that. Banners, here we go. There is his website, so you want to check it out. Eric Reiter studied physics at Sonoma State University from 1977 to 1980, and biology at the San Francisco State University, while doing business as a computer continuum, 18, oh man, I'm getting old, 1980 to 1995, he produced laboratory and automation circuits and software for personal computers. Now he does independent research and consulting. He's published Progress in Physics, SPI, What Are Photons conference in 2015, Foundations of Mind conference in 2016. He also presented at our conference, I think it was in Vancouver, I believe, Vancouver, Canada, and he presented there. He also has technical sculptures, which were received by San Francisco's Exploratorium from earlier on in his career, and he gives credit to his friend for many important consultation donations into this project. So, without further ado, let me bring this down. Let me bring up Eric. Eric, how are you?
Hello, can you see my lecture slides and me?
Yeah, I can. When I bring it up bigger, I'm sure people will be able to see it. But why don't you tell us a little bit about what you're going to be talking about today?
Resolution of wave-particle duality.
All right. So I'm going to let you go ahead. The floor is yours.
Thank you. Well, in the history of physics, it's been called many things. There's quantum mechanics, entanglement. There are many words for this problem, and they're all the same thing. I made a list. Superposition, the measurement problem, spooky action at a distance, the ghost wave, Schrodinger's cat, non-locality problems. So it's all the same thing. All of that is the same problem. So what is the problem? Now, most often, they'll talk about the double-slit experiment to say, well, what the problem is in this wave particle. Well, obviously, light can act like a wave, and the easiest way to see that is the double-slit. But it also happens with atoms and electrons, that kind of stuff. But here's the thing. When you do this wave pattern, what happens is it shows up in discrete points, and people say, oh, a particle hit there. Well, that's the particle property. But the problem in quantum mechanics is much more horrible than that. And this is not the best experiment to show it. What happens is if there's a particle that happens in one place, it eliminates the possibility of the particle happening in another place. That's really the essence of the wave-particle paradox, the wave-particle problem. Actually, I'm calling it a problem because it's not a paradox anymore. I resolved the problem. Paradoxes do not get resolved. But it's been such a problem for such a long time, they call it a paradox. And people think it's not possible to resolve this problem. So going to my lecture slides, there's a better experiment to show this problem. For going two paths instead of double slit, it's better to do it with a beam splitter and detectors that show these clicks that happen one at a time in an electronic circuit, a coincidence circuit that could read, oh, it went this way or it went that way. But that's just the beginning of the experiment. So that shows the particle property. Now, if you were to reconverge this beam and look at it with an interference pattern, you will see an interference pattern. But I forgot to tell you, the source has to be weak, and people go through great pains to make it what they call one particle at a time or one photon, whatever, one at a time source to do this, so that there can be clicks figured out in the detectors. So even though you have a one at a time source and you set everything up where you see it seems to go one way or the other at a beam splitter, if you were then to reconverge the beam, you will still see an interference pattern. And interference patterns can only be made by waves. And they all know that, the physicists. This is the wave-particle problem. The model of waves and particles are mutually exclusive. Uh, Waves go everywhere, and particles hold themselves together. And we know that from other experiments, from the sum of all the experiments that we do. Now, this business of seeing one at a time, I'm going to show you how that's done. But first, I just wanted to introduce, well, what is the problem? This model of, let's say it's the model of the photon, that it has this one way or the other property, or the wave property, or the particle property. There's no way to see how that could be. Many have tried. It's a 100-year problem. They've made up all kinds of parallel universes, a whole list of acts of desperation. We live in a computer simulation, on, to figure, well, what's going on here? Well, I looked at this very closely, and these experiments that were done here with the one way or the other, I'm going to go down and show you that this is really true. It's not really true. It's that it's been done many times. Let's see. I don't have my. Let me see if I can get the actual. Let me bring up another file. I have the other experiments. The people, the past attempts at this experiment were done poorly, to show that it goes one way or the other at a beam splitter. So I want to show you that they really think it does this for good reasons. Now I'm saying it does not do that it's an illusion. This one way or the other property, the particle property at a beam splitter, Eric says is an illusion of something else that's going on, and I'm going to show you. First time this was done to test quantum mechanics, when was this? 1946. They did it with X-rays. They had Poor detectors. Then they did it with light. And these people, I don't expect you to see what's on the screen here. It's mostly to remind me as to what to say. They explained that if such a correlation did exist, it would call for a major revision in some fundamental concepts of quantum mechanics. This is the test of quantum mechanics, to see if light goes one way or the other at a beam splitter. You can barely make out that this is a beam splitter. But then it was redone again with an atomic beam that was illuminated by a laser and put out pulses of what they call their photons. I'm saying there are no photons. The photon is an illusion.
Eric, can you hear me?
Yes.
We're not seeing your screen. I think you're trying to share a screen, but we see your slides. But if you're trying to show us something else, you need to put it on the same screen. We're not seeing that. We're seeing...
All right, hold on.
I think you're talking to some other graphic there.
Yes. Let me try to get the graphic.
No problem. If you put it, just can put it on the same screen as the other one, I think that's the easier way to do it. You can share different parts of the screen.
Yeah. Where did you go? I lost you.
Oh, did you lose me? But you're still here.
I lost the URL of where I'm supposed to go for you.
Oh, okay. I gotcha. Well, we still need to get it on the screen. If there's something you need, you would have to put it so we can see it because we're broadcasting live here. So where your lecture slides are, you want to take whatever your browser and put it on top of that maybe, so we can see what you're talking about.
Yeah.
I'm going to remove that one. Hold on. You're also in twice there. Hold on. I'm going to try to kick this one from the studio and see what happens there. Okay, I got you out of there. So, okay. Well, why don't you just talk to it? Let's not worry about it. Just describe it to us in words.
I will.
Okay.
You see this, my first screen?
Yeah, what we see on your first screen is the CMPS University of British Columbia. Yeah, okay.
The other attempts to do this experiment were done with visible light, and they did it poorly, and like 4 or 5 times. And I can shoot all kinds of holes in the way they did it. The problem is they did not have a decent idea of the alternative to quantum mechanics to know what would work to do the opposite of this, the result of this experiment. The result of this experiment that they get looks like noise. The experiment, it makes a time histogram. Let me go to this one. This is the test to show that you're getting one at a time source. And it's typically done with gamma rays. That's the difference in what I do compared to what other people do. I do this experiment with gamma rays. So let me explain this experiment that is the way it's done in formal nuclear physics to show that the radioactive source emits one at a time. They have a radioisotope in the middle.
Eric, hello?
Yeah?
What slide are you on?
About the 4th.
Okay, right now we only see the first slide.
Oh.
You may be having another slide open. I'm on slide 1. What we see is definition of photon from Bohr quoting Einstein. So you have it somewhere there, and you may have 2 of them up or something, but you're talking about a slide that we only see the first one.
I lost you. I went and I opened up StreamYard a second time.
Okay, you're going to want to maybe close that, but we do. I kicked you out one time because you had 2 of them up. Yeah. So
Me?
I can see you. I can see a slide with the first slide on it. If you have 2 StreamYards, get rid of one. Apologize, everybody. This is what happens. Okay. And worst case, if we lose you, we'll get you back and continue the talk. So, did you get rid of that one? All right. Now, can you find your slides, your lecture slides?
Is the slide changing?
No. Right now we have slide 20. There are 22 slides and we're on page 1. So you must have it somewhere. At the bottom of your screen, you're going to find it somewhere that you have your slides. And when you find those and you find the right ones, you'll be able to move those slides forward and backward. Did you find your slides? It's lectureslides.pdf. Did you find that on the bottom there?
I'm going to share screen.
But you already have a screen shared. Do you want to here's what I'm going to do. I'm going to I'm going to kick your screen from the studio. All right. Now, oops, there he goes. Hopefully he'll join again. So, all right, folks, we're going to just get him back here. Do apologize. These things do happen. One of the interesting things he is talking about, and my father and I talked about this extensively, is this idea in quantum mechanics with the double-slit experiment, is that he said something very important. When you look at, if you go online and you watch the double-slit experiment, you're going to see what he was talking about. All right, he's back here, and let's get him back up here. All right, now can you share your screen again? I think we'll be okay. All right, and we're here with Eric Reiter. Is it Reiter or Reiter? Reiter. Eric Reiter here, and he's talking about quantum mechanics, and I agree with a lot of what he's saying here, and that is when people are trying to do these double-slit experiments, we're waiting for him to get his slides up so that he'll be able to share those with us. He was talking about how when they are doing these experiments, they say one thing and what they're doing is another. The idea that they're actually saying that they're going to shoot one photon or one electron at the double slit is, in my opinion, and I think his, very suspect, especially the way they go about doing it. They basically just keep blocking it out until they get a level where they think it's a photon. So do you have your slides there on your screen there, Eric?
No, I don't.
Okay. Why don't you find those slides? And you mean you're not finding them on your computer there? Do you know where those are on your computer?
Yes, I do.
Okay. Once you bring those up, I'm going to bring you down, and while you're down finding it, I'll be able to see you share your screen as soon as you find that, okay? All right. I'm going to have him there. He is in our green room. I can watch him there. As soon as he gets his slides up again, we'll continue. But what I was saying is, in the double slit experiment, oh, there he goes. See, I just got to get him out of there, and I think we've got it. So let's try this now. You've got the whole sort of browser there. You did the screen share or something. Let's see. Boom. Can you do a display of that or something to make that a little bit bigger? I think you had, like, view or something like that. I don't know if you can right click on it because we're seeing your whole browser. Okay. Again, I'm going to get him. He's getting his slides up. I do apologize for the delay, but we all know in the online world this happens. Even at big corporate meetings, even with, like I said, big corporations. This is the internet, and it's not easy to do these things. So we appreciate your patience. And I think we've got it there. Let's check it out now. Okay, we can do it this way. That's fine. Why don't we start again, get to the, we didn't see from slide 2. So we saw slide 1. Maybe you can go to slide 2. Okay, and start there, Eric.
All right.
Okay,
Well,
start, Eric. I'm going to bring myself down here, and if you can continue and talk to slide 2, and we'll go from there.
right. It's very confusing just when people talk about waves and particles. So I just want to mention that there are two definitions, depending on whether you're in a classical wave or classical particle context or a quantum mechanical particle. A quantum mechanical particle isn't really a particle. It has both wave and particle properties. Just like I said in the first slide, where it can show itself in either of those two kinds of experiments. But classical waves and classical particles are mutually exclusive. So I hardly want to even talk about using the word particle. If you use the word particle, you really should say quantum mechanical particle. But I'm saying quantum mechanical particle is just wrong. The idea of a quantum mechanical particle is to ask you to give up making sense as to how that can be. And they know that. So what has happened in modern physics is that the wave property has been put to a mathematical non-reality. They make excuses like it goes faster than the speed of light, and they put their reality really in the particle, and that the wave property is probabilistic. It's a probability wave. They call it a probability wave. So that's something to watch out for. Now, there are different ways this beam split experiment has been done, where it really looks like a beam splitter. But I did a variation of it where there's a thin detector in front of a thick detector. And it works better. And I do it with gamma rays. So here on my matrix, who's done what? You could do it with light, with gamma rays, alpha rays. That's like helium is what the alpha ray is, and other kinds of stuff. Oh, and I forgot. Down here is the true coincidence test, where you can see if you have one at a time. It's the same detectors, but rearrange it so it surrounds your source to see if it goes one way, you get to click, and not the other way. Then they know it emits one at a time, because what gets emitted is it's pulsatile, it's directed, it goes in one direction in a very narrow beam. And they do tests to know that. And this is how they put together the energy level diagrams of all these radioisotopes. They can see if it puts out one or two or whatever number at a time with this geometry. So who's done what? I'm the only person to do this test with gamma rays at all. And I see the unquantum effect. I'll explain what the unquantum effect is. Who has tried to split the alpha ray? Nobody has attempted to do that except me, and I see the unquantum effect. Everybody agrees on this one at a time test, the way it works. So I may go back to this chart later to review, because there are different ways to do this test. There's three different ways of beam split coincidence, to split the beam, or to just do a coincidence. And then there's different ways of looking, whether you're looking at light or X-rays or gamma rays or what, and who's done what. The important tests, I'm the only one who's done it, who has attempted to split the gamma ray and the alpha ray to test quantum mechanics. No one else has tested quantum mechanics this way in the all-important beam split experiment, except me, to see if quantum mechanics is true. It's counterintuitive, it's almost blasphemy to test to see, well, does an alpha particle act like a particle? I'm saying it doesn't. I'm going to show you the details of these experiments. So what's going on to make this happen? It's like filling cups where there's something in it ahead of time. I call it the preloaded state, where what's coming across space is a puff of near field energy. Let's do this for the gamma ray, for electromagnetism. It's a burst of energy initially directed, so saith Eric. And what happens in the absorber, in the electrons, is that there's a preloaded state and you get to fill it. So it's a 2-for-1 test. You're starting with one at a time, and you're going to see if you can get two at a time. How do you see 2 for 1? Most physicists will say that's impossible. What I'm doing is just looking at half photons or doing some other nutty thing. I'm not. So I trap for that. I measured such a thing. The way you see 2 for 1 is to understand that half of the energy or some fraction is preloaded in the detector electrons ahead of time. So it's like filling cups like this. So what it's about is that you do not see the effect until it fills to the top, and then it all spills. It's a threshold effect. That's why I call it the threshold model. So I'm saying the universe works by this threshold effect. And that's what the experiment says. I'm not just talking. I've done hundreds of experiments to show this. But I'm trying to clue you in as to how I was able to visualize it ahead of time to know that the experiment would work. This is how to understand the preloaded state, the threshold, that you can get a 2 for 1 effect. 2 full pulses. The pulse height that comes in these detectors is proportional to what they call the photon energy. It's also proportional to the electromagnetic frequency. All right, so now this is the true coincidence test, and we're looking more closely at the electronics. There are pulse height filters. We only use the pulses that are characteristic of the gamma ray, the full pulse height photoelectric effect response of the gamma ray. Now, this is set up to just see it puts out one at a time. And when you do that, you put it in a time histogram where the difference in time that happens between the pulses that show up makes this band of, it's a histogram where 0 time is in the middle. So if it goes click, click, goes left, right, click, then you get a pulse on the, a count on the left of the histogram. If it goes the other way, click, click, then it will make a count on the right side of the histogram. If it comes together in time, it'll make a big peak. So any peak in this time difference histogram means that you're doing better than accidental chance. If it's chance, it just makes a band of noise. So what happened in the other people's experiments who did this, they just saw this band of noise, and that's consistent with quantum mechanics. But the detectors were the other way. The detectors were in a beam split coincidence, in a beam split geometry. And they just saw this band of noise. This is the data that shows the band of noise in the time difference histogram to see, well, do the clicks happen together in time? If the clicks happen together in time, it would make a peak. But here it doesn't. It makes a band of noise. I call this chance. This is the result where it looks like it's just accidental chance that it happens either way in time. These other peaks that happen is when they inserted experiments that they knew would make coincidences. So if you start with 2 at a time in coincidence, it will make a peak in this time difference histogram. This is the result of the experiment, the time difference histogram. Whether it makes a peak or not, if it makes a peak, you're doing better than accidental chance. And accidental chance is what quantum mechanics predicts. This is what is expected by quantum mechanics. If you only have one at a time and you split it to go to two detectors, you expect it to just be random in time to show up as detector clicks. So they did this in many different experiments to show, oh, it acts like quantum mechanics. Therefore, quantum mechanics must be right. But they did not do it with gamma rays the way I did. I had to figure out, how do you see through the illusion of quantum mechanics? What is necessary to adjust that experiment to see that it can go both ways at a time to make a peak and show quantum mechanics fails? So I'm the only one to show quantum mechanics fails. I'm the only one to show how quantum mechanics fails. Why gamma rays? Let's look at this bottom graph. It's a pulse height histogram. The horizontal on the graph is how big are the pulses. And so it makes this nice peak, and those are the pulses we use. There is what we call pulse height resolution. So now when you compare to what other people use, they use photomultiplier tubes. Photomultiplier tubes have a wide range of pulse heights, even with monochromatic light. With visible light, you get a wide pulse height distribution, and it's not possible to show the energy argument with this wide distribution. With this wide a distribution, it depends on where you set the pulse height filters. If you set the pulse height filter too low, then you could be counting half height pulses, and you'd say, well, that would favor the threshold model. If you set the level too high, you'd say, well, that's not fair to the photon model. It doesn't work. And people who do these experiments fail to explain how they set their pulse height filters, and they don't show this comparison at all. They're oblivious to the problem. Essentially, you cannot do the argument as to whether it's quantum or classical unless you go to gamma rays. That's part of my discovery. How to see through the illusion of that one way or the other experiment in a fair manner. You go to gamma rays, you have this property where you have pulse height resolution. And remember, pulse height, other experiments have shown, and I agree with them, that pulse height is proportional to the electromagnetic frequency, and that's also proportional to what they call the photon energy. And they use electron volts, and I'll even use electron volts because everybody uses it, and you won't know what I'm talking about otherwise. This is what the experiment looks like. It's not that complicated. It's a fancy oscilloscope. There's the special pulse height filters and amplifiers, and then there's detectors. The detector, I'm going to go to the next slide. The detector, this is how I do the experiment. The detector is a crystal of sodium iodide that's surrounded by aluminum foil that gamma rays can go through there, and in the crystal it makes a tiny flash of light, and a photomultiplier tube picks up the light and makes a pulse of current. And so there's two detectors. The best way I found to do this was, instead of using a beam splitter, was to put a thin detector in front of a thick one, and that separates the energy. It's the same thing. It does the same thing as a beam splitter, but in a sense, it combines the idea of separating the direction and putting the detector all in one thing by picking out some of the energy in this thin detector and then see, well, does it go through and make a click in the next detector? Well, by quantum mechanics, it should not. So we do it, and there are only a few radioisotopes I found that work. I'll explain that soon. But here's the experiment. I'm able to see everything on the oscilloscope at once. I'm able to see the pulse heights, that they're all well-behaved pulses, as if it was an oscilloscope. I'm able to see the pulse height histogram to see the distribution of heights, and I'm able to see the timing histogram. And I read right from this graph how many happen in this window of time. How many happen over the duration of the time of the experiment. And I'm able to compare to chance. So at the bottom here, this is the chance calculation, where I'm sort of covering, there it is. The whole experiment is about comparing to chance. There's a rate in the first detector, no coincidence, just the singles rate. There's a rate in the second detector, and then there's this time window. The time window is what I use to, in my big peak here, how far apart in time are these clicks. So I use the same time in the experiment where I read coincidences in this chance calculation. That's how it's done. Other people who have done this experiment to see in that true coincidence test, they compare to chance in the same way. So we do the rate in one, the rate in the other, the rate in the first detector, the rate in the second detector, times the time window, and you get a coincidence rate. Oh no, a chance rate. What is the rate that detector clicks would show up just by accidental chance, which is what quantum mechanics would predict? Well, I get a number. Then I'll compare that to the experiment. The experiment is able to read straight away, there's some number in such a time, I get some rate of clicks per second in coincidence. But now I have to remove the background. There are coincidences that are made when I remove the source, remove the radioisotope. There still will be a few percent of coincidences that happen just from outer space. So you subtract that, and then I get a corrected rate, and then I compare the experimental rate to the chance rate. I hope you're following me. This is the most important part. The experimental rate to the chance rate, no one has seen anything other than 1 for this ratio. For when they split their photons and see, well, is quantum mechanics true? I see 33 times chance. This is a robust effect. It's a strong effect. So I call it the unquantum effect. And I've done it 100 times, hundreds of times, with different isotopes. So let's go to the next slide. This is another radioisotope. The first one was cadmium-109. It puts out 1 gamma ray at a time. This one is cobalt-57. It also emits 1 gamma ray at a time. And we know that from nuclear physics labs, and I test it here. I'm able to rearrange the detectors and see that it really does show up 1 at a time in the true coincidence test. And then I rearrange the detectors to go 1 detector in front of the other to see in the beam split test Can it make two at a time? Which it should not do by quantum mechanics because it's a photon. And everybody else thought so. But I see it can go two at a time. So it's a 2-for-1 effect. I'm reading full height pulses. And I'm saying it can do that because there was something there in the detector ahead of time that loads it up. We get a 2-for-1 effect. So this experiment was about 6 times accidental chance, which is great. You can see in the wings of the histogram that there's a chance rate. And I can measure the chance rate if I want. I do it often to see. There are 2 ways to measure the chance rate. By this calculation I showed earlier, or by looking at what happens out of time and reading the rates in the sides of this histogram. And it comes out with about the same number. So let me explain what it is about these radioisotopes that I discovered. That you have to use a radioisotope that has a high photoelectric effect efficiency in order to see through the illusion of quantum mechanics. Because the unquantum effect is about the photoelectric effect. Now, other people have worked out the different mechanisms as to what goes on inside the detector to make this graph. This graph is on the horizontal is the gamma ray pulse height, which is also what they call the energy, photon energy, horizontal. The vertical is the efficiency of absorption in the detector. How efficiently will it make these clicks on our oscilloscope? There are other mechanisms besides the photoelectric. The graph of the photoelectric effect is this sloped line. Then here's the Compton effect. It goes across. And then there's another effect over here. Now, the radioisotopes that I use are, here's the cadmium 109 and the cobalt 57. They have the photoelectric effect dominating over the Compton effect. When I first did this, I was using radioisotopes out here, and I did not see it defy quantum mechanics. And that's what other people see. You have to know what's going on, how to set up the experiment. This was very hard to do, to figure this out, that you have to have the photoelectric effect dominate. In most of the physics books, they use this radioisotope, cesium 137, to look at, to see if there's 2 pulses in one detector. It's called a sum peak, and that happens by accidental chance. And most of the isotopes are out here. They're stronger. So there has to be several things about these radioisotopes. They have to have a reasonable lifetime. Very few of them do. They only have to be putting out one at a time. And they also have to be down here in this lower frequency region. That's asking a lot. There are only a few radioisotopes to use. And I was lucky to find them and use them to see the effect. And I was able to see it with different detectors up here. So it's not a special case where it's just one radioisotope. I have seen this effect with a total of 4 radioisotopes, depending on which detectors I use. So, right, here's a whole list of the different ways I've done the experiment. The sodium iodide scintillator, a different kind of crystal scintillator, bismuth germanate, high purity germanium. That's what most physics labs use. But the high purity germanium detector has less photoelectric effect efficiency, but it has better pulse height resolution, and that's why they use it. So in a case here where you would think it would work best, it even works worse with the better detector to see the unquantum effect, because most physics labs use this detector. But sodium iodide is a very popular detector. It's been around since the 1950s. So which radioisotopes? Here are the 4 radioisotopes that I tested with some success. There are different geometries of how to arrange the detectors. In the beam split geometry, I've done experiments that look just like a beam splitter. And I've done it where what I call the tandem, where there's a thin detector in front of a thick detector. I've done it those ways. Then there's just with one detector. It's possible to see 2 pulses in one detector. It makes a bigger pulse when that happens. The single detector sun peak test. So I was able to see that. There's a way of gating one detector to look at the pulse height spectrum of another. Done a bunch of tests like that. You see extra things, extra properties of how the gamma rays scatter. And then I've done it with 3 detectors, to use one detector as a trigger where there was a large gamma ray, and you can tell by the pulse height, and I used that to trigger, and then the other 2 detectors were in coincidence. That was very convincing. Then there are all the tests I've done to eliminate artifact. Like, did I discover a new kind of stimulated emission? Were there echoes in the photomultiplier tube? Is there lead fluorescence? On and on. There are a whole list of problems where people throw it at me and say, well, did you screw up any number of ways? And so I tested for these problems. And then there's different electronics. I tried all the different kinds of electronic hardware that people use for this test. And the method that is best is with this fancy LaCroix oscilloscope that I showed pictures of earlier. Then there's more tests I've done. See, all the components of my argument make sense. The way I had to make sense out of it, I kept doing experiments. What if the beam splitter was cooled to liquid nitrogen temperatures? Would that make it work better? Well, you would think so. Well, I tested it. It did work better. It was 1.5 times better. Good ratio, 50% better. When it was cold, I did tests with magnetic fields on the beam splitter to see diamagnetic and paramagnetic properties. That worked. Functions of angle. I did some tests that worked with a special source. That special source was, I did an incredible set of tests where I was able to purchase cadmium-109 in a liquid form and then electroplated it to be smaller, to get more cadmium-109. So my initial intent was to just concentrate it, and I was able to do that. But then I realized I have 2 different chemical states. I have a metal state and a crystalline state. The normal form when you buy this is like a crystal. They let it dry. They start with liquid, they let it dry. It's a solution in water. They let a water solution dry away. They make a little crystalline patch. Then you buy it, they send it to you. I'm only able to buy license exempt sources. So I did this trick where I bought it in liquid form, where I could buy several of them and then concentrate it to get a stronger source. But then I realized in the process of doing that, I changed the chemistry to a metallic state. So I tested, does chemistry matter? And I found that it did in a big way. That the crystalline state worked better than the metallic state. I forgot by what ratio, several times better. It was really great. Then does distance matter? How far away do you put the source? Well, it should matter by my model, and it did. It did matter. And it made sense depending on whether I used a higher frequency gamma ray source. The cone of light comes out by a well-known equation in optics. The width of the cone of light is a function of the frequency. So if it's a high frequency gamma ray, it comes out narrower. And what it seems to do is fit the size of the electronic absorber. So if you have a narrower beam, you have to pull it back, and then it works better. If you have a wider beam from a lower frequency source, you push it closer. It all worked. It all made sense. So I did all of these experiments to do functions of physical variables to see what makes the unquantum effect tick, what makes it work and what makes it not work. I sorted the whole thing out. I did all these experiments from year 2000 to mostly 2005. I've not done this experiment successfully for maybe 6 years. And I'm revisiting it now to try to see, to make it work again. This next slide is the triple coincidence test, and this is the actual data up on top. And that's cool. It's a bit complicated to explain. I just want to say that I went through great pain to do this many ways. All right, this is the kicker. To resolve the wave-particle duality paradox is not just about light. It's about atoms. Atoms are supposedly diffracting. This was done as early as 1930 by Esterman and Stern in Germany, and earlier with electrons by George Paget Thomson in England, and these other Americans. Anyway, I found it easy to work with alpha rays because there's a smoke detector that you can just find at the hardware store that has a radioisotope in it that puts out alpha rays. So I was able to collect several of these, and I was able to find the alpha ray detectors. They're special detectors. And I put it together in a vacuum chamber to test, well, does the alpha particle go one way or the other in a beam splitter? I hope you see this. No one's tried this at all. The setup is very similar to the work done in Rutherford's lab for the model of the nuclear atom, where he used alpha rays bouncing off of a gold foil and to look at the angles that the alpha rays scattered. But I'm just looking at two directions, whether it goes through or reflects, and I'm reading it in my coincidence circuit. So there are a few ways to do this test. To split the alpha ray in half requires Other people have done this experiment, have tested what does it take to split the alpha ray in half. They do collision experiments, and they found it takes 7 million electron volts, 7 MeV, to make 2 deuterons, to split it in half. 2 deuterons are put together, so they say, to make helium. Now, I only have 5.5 MeV of kinetic energy that is emitted in spontaneous decay of americium-241 to make an alpha ray. I do not have enough kinetic energy to split the alpha in a conventional sense. So it's valid, reasonable to see if I get 2 half-height pulses, and I do. That was the first thing I did. And what does it read? Compared to chance, over 100 times accidental chance. Terrific result. I did this experiment 100 times. There were 4 different vacuum chambers where I rebuilt the whole thing. It was so sensational that I rebuilt the whole experiment top to bottom 4 times, different detectors, different ways to do it, and then all different kinds of beam splitters to see if this was true. I hope you hear me. Then there's the full height pulses. What happens if we only look at full height pulses? Well, I had to go through a bunch of programming to program the LaCroix oscilloscope through its bus, and wrote a program to read the detector pulse heights and then regraph it here. The horizontal on this graph is the pulse height of one detector. The vertical is the pulse height of the other detector. The half height pulses are here. The full height pulses. Now, when you read compared to chance, it was 6 times chance. So even if you use the full pulses, it's a sensational 6 times accidental chance. All the pulses are perfectly shaped. I had everything graphed here. It was a sensational result. Well, how can it be? It means the helium is not always a particle. It's the helium nuclear wave function that gets split. Now, they've known about the wave properties of helium, like I said, since 1930. But this is another very interesting experiment done by somebody else, where they can see they can focus helium to see its wave property, but they also can see that it goes straight through. It's a set of slits, circular slits, that makes a lens. So they have a oven of helium. It radiates out from left to right, and they're able to see on a screen where does it land, and they get this pattern. The middle is the wave property, and on the side is the particle property in the same experiment. So the combination of this experiment and my experiment is telling us that atoms can take on either of 2 states. It could be a wave state or a particle state. And we call it a soliton, where it could hold itself together or it could lose that ability to hold together and show itself as a wave. This is a subtly different idea from complementarity. So go back and think about it and look at my website. Everything I'm showing here is on my website, and all the extra details are in papers. So if you don't understand it, it's all explained in detail. Now, I did the theory first before the experiment, and there were important components. I was able to derive the photoelectric effect and the Compton effect without wave-particle duality. This graph, don't let it intimidate you at all. I'm just doing a very simple thing with these equations. I'm looking at the ratio of our physical constants. Planck's constant to the mass constant, the mass of the electron. There's the H to M ratio. All I'm doing in these equations is rewriting the ratios into just one symbol. I'm calling it a Q. So I'm starting with the de Broglie equation, which is a matter wavelength equation. The wavelength is equal to Planck's constant divided by mass times velocity, momentum. Now, the reason I'm doing this Q thing is that these are the experiments that show wave properties. I'm saying, what is the message of the experiment? The way other people look at this is they don't realize that the M may have come from a different experiment. The H may have come from a different experiment. What is the message of each experiment? The message of each experiment, when there are wave properties, is that the ratio of the constants H, M, and E, there's three ratios. There's the H to M ratio, there's the E to M ratio, the E to H ratio. The ratios are what is quantized, not the individual H or M or E. I call it, in fun, the ratio trick. It's not really a trick, it's a realization. I call it the ratio trick. So when you look at the photoelectric effect and the Compton effect, all these effects, you can now see what is the experiment telling us. And this is how you can visualize that the matter wave can spread out and maintain the ratio and load up at the detector. In this drawing, I'm saying, let's take an electron. I'm saying what the electron is like a puff of this wave. It has a beginning and an end, and we're radiating it across space in a beam experiment of electrons. So we're going to just look at, well, what is this electron in the threshold model? To start with, it'll have a whole E, a whole M, and there's Planck's constant associated with it. But as it spreads, you can take some cubic volume of this wave, and the ratios of those constants will be the same, even though you have less. To be less charge than everything you started with, less M, less H, but the ratio is conserved. So in this way, you can have sub E charge in your absorber, and it can load up. This is my discovery about the physical constants, that the ratios are discovered. This was the most important part This discovery is every bit as important as the experiment itself to understand the ratio trick. This is how I knew that the experiment would work. I figured out the theory first and then did the experiments. Now, for more of the theory, I'm not going to go through all this, but you can go to my website and you can see how I derived the photoelectric effect and the Compton effect and Planck's black body distribution. I did some equations with spin and pair creation annihilation. So I did equations of all this. I'm not just an experimentalist. I do theory, and I had to do a historical analysis of many books and papers to see what is it people did and what mistakes were made in their experiments. So now we're going to review. I'm going to go back to this slide we saw before. Who did what? Beam split experiment with light. Others did it where they saw just quantum mechanics. If you do it with gamma rays, the way I did, you'll see the unquantum effect. If you do it with alpha rays, I'm the only one who did it. Both of these cases, I'm the only one who did it. You see the unquantum effect. This thin detector in front of a thick, I call it the tandem geometry. No one else has tried it except me with gamma rays. They did try it with heavier, with massive particles like protons and neutrons and cosmic rays. They use this geometry and they see quantum mechanics. They're just looking for quantum mechanics. And that's what I would expect also with such heavy particles, so-called particles. But for gamma ray, I'm the only one who did this geometry. Because it's not supposed to work by quantum mechanics. And no one will publish me as well, because I find things that are against quantum mechanics. The true coincidence test, everybody agrees on how that works. Me and quantum mechanics people. I'm not sure what else I should say now. I'd like to call for any questions and review overall. I went through a lot of things, maybe too fast. I'd like to open up for questions.
Yeah, can you hear me?
Yes.
Okay, well, I can start it out. If you do have questions, what I would ask is, let me see here. I think I have something there, how to put questions. Here we go. If you want to have a direct question or comment in the chat, if you're not in the green room, please put question or comment. I'm going to start it off a bit here. First, I've got a couple of things. First of all, I agree completely. My father and I have been looking at the double-slit experiment quite a bit. And one of the things that was really shocking to me, which you brought up, was when the mainstream is doing these experiments. First of all, it's not done a whole lot, which is pretty amazing. It's such an important experiment that quantum mechanics is based on, and all this crazy history erasing and all this other, the consequences of this experiment are huge, and yet the number of people who do the experiment understand what's really going on with the experiment seems to be minuscule. And one of the things that I noticed, and you made a comment about, was that when they try to pretend, I call it pretend, when they try to pretend that they're getting one photon or one electron at a time, all they're doing is taking a beam and bringing it, getting, blocking out less and less and less until they get to what their threshold is, what they say would be a photon. How is that a correct observation of how they pretend they're getting one photon or one electron?
No, no, not really. They go through much greater pains than that.
Okay.
They've made an atomic beam, and they irradiate it with a laser. They lower the rate of the atomic beam to what looks like one at a time for that, and then they see what light gets put out in a photon sense from those atoms. And they'll even set it up so that it puts out two of their photons, and they'll see it in two detectors, and they use one as a trigger. So they have gone through great pains
Okay.
to see that it's indeed a one at a time source.
Okay. Now when they call it a photon, what are you thinking that is? Is that a one particle, or is it quanta of particles?
Right. There's great confusion over the word photon.
Right.
The definition of the photon is phenomenological, just like my first slide.
Right.
It's that by the photon model, it should show one way or the other at a beam splitter, and by the photon model, it should also make wave properties. And again, there's no way to see how that could happen in space and time. It's shut up and calculate, give up understanding, just play it by the rules kind of thing.
Right.
And it's not a thing. It's a phenomenon of these two experiments. And this idea goes way back. It's even in Bohr's book, where he explains from his arguments with Einstein. I have the book. So it goes back this far. If a semi-reflecting mirror is placed in the way of a photon, leaving two possibilities for its direction of propagation, the photon may either be recorded on one and only one of two photographic plates situated at great distances in the two directions in question. Or else we may, by replacing the plates by mirrors, observe effects exhibiting an interference between the two reflected wave trains. Atomic physics and human knowledge. What is this? So, 1958 book. It even goes further back with collapse of the wave function explained in Heisenberg's book. It has not changed since then. This idea of the photon model having those two properties of being able to hold itself together, show itself as a particle, and also it diffracts and interferes. People think of photon as a particle of light. It's not true. The definition, the idea of the photon in physics is that it has both wave properties and particle properties crammed together in a way where nobody understands it. Yet they say the world is like that because of these experiments.
So what you're saying is mainstream science talks about it, has no idea what it, how to explain it, but then they go around making mathematical equations about it. And
Right.
then not only that, they go on top of it even worse and make philosophical assumptions on top of that. And that's where you get into all this spookiness and this action at a distance. So they are reaping what they're sowing, which is they will not answer the most important fundamental question. And so therefore they get themselves into an impossible situation.
Right. They've embraced the paradox instead of trying to resolve.
Yes, that makes total sense. Another question. I noticed you talk about you said during your talk. I heard you say alpha ray and alpha particle. Now, can you explain to me that interchangeability? Is that the same problem or paradox, or do you say that with a different meaning in mind?
Well, it's just two words for the same thing. People have talked about the alpha. Uh, it's used interchangeable in physics, but to me, it's not a particle. I'm able to split it like a wave. Other
Mm-hmm.
people have called it the alpha particle, and I'm saying it's a helium nuclear wave function. Uh, there still is such a thing as particles, and helium can even hold itself together as a particle in solid states. But it has this ability to show itself as a wave, where it really does smear out and spread in several directions at once. So that's what was really tricky about all this, to understand how entities with rest mass, like helium, can show itself in the wave or particle state. So splitting the helium in the beam split test, that was the killer. That
Mm-hmm.
was the most important thing to see how to do that.
Mm-hmm.
Uh,
Okay.
Go ahead.
Yeah. Okay. And the question then too becomes when you say, of course, photon. I agree. You can't have one particle carrying frequency. It just doesn't make any sense. The photon. But when you talk about when you're talking about it, are you talking about something like an ether? Are you talking about what? Or do you have no? How do you say? Conclusions to that, because you do talk about do talk in a way that it's wave like, so it's a wave like in something, a wave of part. What is that?
I'm not making that distinction yet.
Yeah, I got you.
Yeah.
Okay, that's what I thought. I didn't hear that distinction, and you never really led on to that. So that was a question. I'm going to hit a few more, and then we have some questions for our audience coming in. We have people in the green room too that can come up. So, how did you say you solved? Could you put it in a way, because technically a lot of people aren't as heavy in math, but can you give us a sort of a higher level view of how you say you have solved what they say, quote unquote, is the wave particle duality? Can you give us more of a colloquial explanation? Or is that too hard?
Well, I can give a few simple examples, like
Okay.
to say it happens with sound. Uh, there's a commercial with Ella Fitzgerald, and I could even bring it up, where she sings and breaks a wine glass.
Right.
Well, if you didn't know about the sound, you would think a bullet hit the glass
Hmm.
because it happened suddenly. But it was waves that went across space
Right.
that built up and broke the glass.
Right.
So that's the accumulation hypothesis, the loading theory, the threshold model.
The
That
threshold model seems to be very close to the photoelectric effect, in the sense that the only difference is what you're saying. That's a threshold. You're not making a claim that it's necessarily even a photon, but that is there's a force there. That force has to get to a certain point. And something. And what you're also saying is where it's hitting is important as well. I had noticed you in your how do you say analogy is you have cups, and those cups are somewhat full. They're not empty. And then when this comes along, it gets to a threshold until which it happens. Just like you're saying, the sound gets to a threshold where that vibration gets to a point where it becomes critical. It seems to be, is that a good sort of a easy way to explain what you're saying about the threshold model?
is the easy way to explain it. but there is some confusion with the photoelectric effect,
Right.
where there is a threshold in frequency, and that's a very different thing that I'm
Right.
talking about.
Right. Right. Okay. All righty. Let me see if I can get to some questions here. Let's see. But okay, I think we may have talked about some of this. This person says, "Great work to you. It simply shows the photon particle does not exist. It is just based on bias and belief. But what is an atomic particle? What part of the atom has a threshold?" That's a question.
Wow.
Is that too, or is that just
We'll
that's a big question.
We'll sort this out later. Other scientists have successfully shown wave properties of charge, that is to say electrons. They've done
Right.
it with neutrons and protons, atoms, and it looks like all the way up to diatomic sodium. It looks like they did those correctly.
Mhm.
There are other experiments done by the Vienna team, and I've challenged them, and I think they just did the experiment all wrong. I've had correspondence and I did calculations, and I posted it on my papers. They tried to say that they can diffract buckyballs, like thousands of atomic mass units, kind of real particles, and they go through all kinds of contortions in their experiment to show that it's true. And so I'm calling them down, that it doesn't really happen. So the kinds of particles, so-called particles that can diffract, and they're not really particles if they diffract. I don't know what to call them.
Right. Right.
Uh,
Right. I think that's one of the general problems with experimentalists. The problem is they're going into it sort of with kind of with a model in their head. They then go and do the experiment, and then they start making up models to explain it without trying to look at a bigger context. One of the things that I think your work is just so great is the variations you do. I don't see that going on. What I see people do is they'll repeat the old double-slit experiment. They won't try anything. They won't make any try to think in their mind of maybe here's a problem or can I do something different. They don't. There should be people doing this experiment like you all over the world, because right now what they do is they do their experiment, they get into the ridiculous paradox. That's, of course, a paradox means something's wrong, it's got to fix it, and then they have all these conclusions, and then they debate all this stuff, and you and me and many other people are standing there pointing at the experiment going, you don't even know what's going on here. I mean, that's what it seems to be.
right. Well, there's a tell. You can tell right away that they're using the photon model to justify the photon model, because they're describing their experiment in terms of photons.
Yeah.
Right
Yeah.
away, you could tell how biased they are, what a big mistake they're making.
Right. That's absolutely true. Okay, I've got people in the green room too. I'm watching the questions here too. I think some of them have already been answered. I do see Ian Cohen wants to come up here. Let me get this question off the screen here and bring up Ian. Okay, Ian, how you doing?
Hello, very well, thank you. Thank you very much. My point is somewhat philosophical. I have been considering for some time the ultimate reality or otherwise of the quantum theory. I think even Max Planck, at first anyway, said that his hypothesis was really an artifact to avoid the ultraviolet catastrophe. And I fear in a way that by conventional physicists, they may have created a sort of a monster, a bit like what Albert Michelson said, when he saw the theory of relativity and being attributed to his early experiments. He feared that he may have created a monster. So I'm just wondering if you'd care to comment on that, because in view of all the paradoxes that have arisen and the wave-particle duality, and which you've endeavored to deal with, and so on. Is there any ultimate reality to a lot of this, or is it really, hypothetical speculation which has been extrapolated inadmissibly?
Well, look, Now we know the world is not crazy with these experiments in theory. Let me just say about Planck. Planck did many papers, and it turns out he did something like quantization of energy in 1900, but in 1911, he did continuous absorption and explosive emission. He did the loading theory in 1911. And actually what I'm doing is an extension of Planck's second theory. He even did a third theory. So he kept working. These people were all great, but they're up against a very difficult illusion to break through. And also the accumulation hypothesis, there were three names put on it. In your textbooks, they call it the accumulation. In history of physics, it was originally called the trigger hypothesis by Leonard. Then there's the loading theory. Millikan called it the loading theory. And then I call it the threshold model, perfected thing. So there's a history. Before quantum mechanics, there was the loading theory. They were considering it. They knew about these wave particle problems. At first they thought the photon was nuts. Millikan thought he was making a big mistake. So in Millikan's book of like the late 1930s or early 40s he talks about the loading theory, but he couldn't understand how it could work. And ever since that, I've looked at hundreds of books and papers and trying to see this history. Ever since that time when Millikan couldn't understand it, people have crippled the idea of the loading theory, and they explain it in a way where there's no such thing as a preloaded state. They do an experiment, and they'll cite it in your physics book to convince you that quantum mechanics must be right. They'll cite the experiment of Lawrence and Beans of 1928, where they tried to find how long does it take to load up, to do the loading. They were considering the loading theory. And your textbook will say, oh, it happens in a nanosecond. Well, that's not what happened. The experiment had a wide range of times, and there are different ways of doing the calculation, but they make it sound as if there's no such thing as a preloaded state. There's only one time, the 1 nanosecond, and it has effectively brainwashed all of our physicists to not use any kind of accumulation or loading theory at all.
So the way I look at that is it takes time for these to happen. I think there's this idea in physics and experiments that I know my dad, when we're working on our particle model, he was looking at electronics and he was bringing graphs to me, and I would try, what are you doing? Because you think of, here's a state you start with and here's an ending state. They don't look at how that happens in between. And what he was doing, he was graphing what was happening to get to that state. And it seems like when you're looking at what you're doing, Eric, is that you are saying, okay, these things happen. It is a process. And what you're saying, there's a threshold. That means there is a time. There are things that you don't just go from here's what happens, here's the end, here's the interference. You have to look at all the things in between. One of the things I thought really fascinating was a photonics expert at the University of Connecticut talking about photons, right? Just light, not even photons. One of the things he wanted to do, Eric, was he said if you could set up an emitter, because they say they can set up one photon emitters, right? He said his experiment, which he never did, was to take 5 1/5 photon emitters. That is, here's an emitter, here's a second one, here's a third one, here are 5 of them. Each of them output 1/5 of a photon. Point them at a 1 photon detector. And if the detector goes off, all bets are off with what a photon was. And he said, we don't know how light's emitted. We don't know how it travels through space. When it gets to our detectors, we really don't know how that's happening. He's talking about in a physical sense. And what I think you are starting to do is you're trying to experiment with lots of different variables, lots of different mechanisms, lots of different, how many times have you redone this experiment? And what you're saying is you're finding that you get to a threshold and something happens. Is that what you're saying?
Yeah, it's a threshold effect. Planck's constant is true, but I'm giving a different definition to it. And this guy who says fractions of a photon, well, that's just gobbledygook. I don't know what he's talking about. There is such a thing as a photon worth of energy being emitted. I'm saying that the emission from an atom or whatever kind of complex it is, when it comes out, it's initially quantized, but thereafter, for light, it spreads classically. So there's that kind of a suddenness that happens. And there's also a suddenness in the absorber where it loads up to a threshold and then will emit a charge and show itself that way. So there are these two kinds of suddenness that happen that gives the illusion of particles going across space.
But then again, when you're saying the illusion of particles going across space, you're saying, is that you're not saying how this happens. You're not saying you said earlier to me, if I understand it right, you're telling us that you Eric are not claiming to say how this travels through space. You say classically, but you're not saying it's particles moving, it's waves in a medium moving. You're not saying anything about that.
I am saying it. I'm just not caring whether it's waves in a medium or not.
Okay.
It's a wave. It's spreading with such time and space understandings, but I'm not covering whether it's a disturbance in a medium or whether it's just propagating its own medium.
Right. Gotcha. It doesn't matter. It's spreading out. This is what's happening. How that's happening is not relevant. It's more of what it's doing when it comes out, and then when it hits the detector, what's really going on. Do you think? I'm sorry. Go ahead. Let me get back to Ian. Ian, did you have any more comments on this?
No. I think I'll leave it at that. But thanks very much for the discussion.
So what was I going to say? I forgot. I'll I'll remember. Let me see if I have we do have some more questions I do here. This is an interesting, do you have any reference for your work? That's on the website, is that correct? I noticed that you had one called thresholdmodel.com, but that's no longer active, is that correct?
No, I have both. There's two websites.
Because I tried thresholdmodel.com and nothing's coming up, or am I wrong?
Well, it works for me. Anyway.
Okay, let me try it.
Unquantum.net. There's unquantum.net and thresholdmodel.com.
Okay, yeah, I think they go to the same. Okay, yeah, both of those go to the same place. I just checked. Okay, so that was a question. Let's see here, some more questions. Anybody else in the green room want to speak? No, I see James Keen's there. Let me question. Okay, one more question I saw above here. Hold on. I think it had to do with solar energy, which was just actually because you're doing so much of this. Oh, here we go. Somebody, interestingly enough, said, does your work provide possibility to make more efficient solar cells? That is, you are doing real experiments here. Is that something that you see as possible or related, or you just have no clue?
Well, when you do fundamental physics, it affects everything.
Of course.
Like going back to the time when electricity was discovered and saying, what can you do with electricity?
Right, right, right.
So yes, it will have plenty to do with better solar cells.
Okay, okay. Well, that does answer that question. Let's see here. Is emission from atomic processes different? Okay. Here's one from Jim Marison. Is emission from atomic processes different from radio?
It's mostly about frequency. Radio is a lower frequency part of the electromagnetic spectrum. They're both electromagnetic. Gamma rays and radio, the whole thing. It's visible light. They're different parts of the electromagnetic spectrum, but there's more of a pulsatile nature that I'm taking advantage of for the gamma ray to see through the illusion. Like, if you try to do this experiment with visible light, I'm predicting it would not work. You would not see through the illusion. It's too mushed out. It's too fuzzy. So there are properties that emerge in the way the frequency of the electromagnetism interacts with charge that are very different for the different parts of the spectrum. So, yeah, the first thing is to understand that gamma rays is just a high frequency electromagnetism, and it will spread in all directions just the way a radio wave will. But initially, from the source, it comes out in a burst. So what I'm doing, it's a near field effect.
Mm-hmm.
I found that you have to be close to it, and that distance matters.
Right. Okay. I have a question. Where did the word unquantum come from? I know is it just simply against the not quantum? How did that come about? Why'd you pick that name?
Right. Because it's against quantum.
Okay.
Quantum is a mistake. It's nothing is quantized really. It's thresholded.
Right.
And the idea of the threshold includes phenomenon that will look like quantized, but the idea of quantization excludes the preloaded state.
Okay.
That was the mistake.
Okay, I got you. I have a question. The interference pattern, where they are claiming the big thing is you have the one photon going through, and it's still making a pattern that's in what they call an interference pattern, even if it's going what they call particle at a time, versus doing just a light beam or wave. How is that explained or how do you explain it with your experience with this experiment, which is very extensive? Probably, I would say you have more experience in the experiment than anybody on planet Earth. So how would you talk about that interference that they are describing as one with particles versus the other with wave?
It goes across space as a wave. There is still an interference pattern, even though you see spots on the screen. What makes the spot is that it loads up and shows itself discontinuously, but the wave went through both every place at once.
Okay, this is something my father and I actually believe is true as well. Is that what's really happening is they're sending this quanta, or they call it quanta, and it's what we see as a detector is just simply where the threshold is, but there's other stuff happening. It just doesn't hit the threshold. Is that what you're saying?
Right.
Yeah, you know what? You and I and my father agree 100% on that. That was one of the we came up with the same, because we have the difference with what my father and I are working on is that you're not worrying about what is actually moving. We do have what we think is actually moving. And our claim is that when the experimentalists think that one spot is, thresholding, as you say, on that screen, it's not that it's just there. It's just that has hit the threshold. And if it's over here, and if it just because of the way it's going, the threshold's going to be over here. But if you were to have how do you say, a more fine grain thresholds around, you would see, oh, it's not the only thing that actually is hitting there. It's just that it reveals itself because, like you said, in the threshold model, it gets to a sort of threshold at that point. Okay. All right. Very good. Let's see if we have any more questions here. Oh, here's a comment. Oops, that's not the right comment. There we go.
I couldn't hear what you said.
Sorry, that's my Alexa thinking I talk with her. So here's a comment. I would say that the burst of light wave doesn't disperse. It's like a wave traveling through Newton's cradle, which travels as a straight line, does not disperse. But I think you say differently from that, right? Because I think you're saying it goes.
Well, it depends on which experiment. If you're talking about visible light, where it goes through, it has to go through both paths to
right.
get the interference pattern.
Right.
It has to go through both paths. So you will not get an interference pattern unless you have a spread out wave. And what's showing itself as a particle is just the local effect of the detectors.
Okay. Right. Okay. That makes sense. All right, here's another question. Again, I'm not necessarily saying these questions make sense or you can answer them, but people are putting up there, so I want to put them up here. Is your photon a solid particle turning on itself on a trajectory, turning at a frequency measured? I mean, you don't have a photon, right? I don't think.
Right, there are no photons.
Right. Okay, right. I agree. I mean, a photon... at least the concept, the way the mainstream talks about a photon, and to me is impossible. You can't. I mean, even Newton tried to do it in some way, right? He tried to say, well, I'm going to try to make a particle that's going to be light, and he had to make them different sizes. You know, how does that work? So, okay, that's what I thought. All right. Did you want to make any closing remarks? Let people know anything. What are you doing today? You said you're working again. What's your future work on this? Because first of all, it's amazing. It's just incredible work. What are you doing now and into the future? Do you have future plans of what you're going to be looking at?
Yes. Well, I've not done the experiment for maybe 6 years. I'm returning to it and trying to see how to make it tick again. I'm trying to make the experiment work for other people to see if they could just take apart a smoke detector and use americium, and also how to replace that thin detector that I use that worked so well. It cost a bunch of money to have that made for me.
Right.
So I'm looking at different crystals and detectors and trying to make it so other people can reproduce it easier.
Right.
I have a friend in Finland, of all places, who I have sent detectors and equipment to, and he is trying to reproduce my work. So that's big news. I'm finally working. I have a student who's attempting to reproduce the unquantum effect. We'll see if he can do it. The other thing I'm working on is a completely different project. I call it the Secret of Life project. I can aim the camera over. It looks like a terrible mess, but I'm working on a way of interacting microwaves with a biophysics experiment to see if I can tune in to control an enzyme reaction to turn it on and off and control life with electromagnetism. And there are connections to the unquantum effect as to why I'm doing this, but I prefer to leave that out for now.
No, that's great. That is amazing. Your lab is simply amazing. My dad has a small little lab in his room that he works with a very, very, very sensitive voltmeter. But I want to thank you because we've come to the end here. I want to thank you so much for your presentation. The other thing too is what I would suggest is that maybe I'll contact with you, but we have groups on our website, and I think there would be people. I know of another guy. He's a young guy, Chris Ekman. He is an experimentalist at heart. And he would be a person that I could get you in contact with who loves doing experiments. I think he worked at Stanford Linear Accelerator, but he's been in our group. He's not a mainstreamer, right? He is a person, he worked with Brown's gas, and that got him interested because they couldn't explain what was going on with Brown's gas, where, you could put your finger practically in a flame and the thing would go through tungsten. So he is a person that loves experiments. He's always looking for them. So maybe I can get you hooked up with them. But it'd be interesting too for us to maybe start a group on our page. What's good about our new web page is that if you start a group and you make a conversation in that group, we have an activity like Facebook, and anything that's said in any group pops up at the top, and those things start, keep popping up there. So we'll see people making conversations. You talk about it, and other people will be interested. So we should probably talk about the experimentation with the double slit to see if other people will be interested in reproducing that. So, well, thank you so much, Eric. I really do appreciate it. Okay, and I hopefully have you back again sometime when you have some.
Thank you.
Okay, thank you so much. Again, that's Eric Reiter, and you can go to his website at unquantum.net. You can get in contact with him. We have a profile. In fact, I think if you put his name in with quantum mechanics, you'll get his profile on our Science Woke webpage. You can look him up there. You can look him up in our Wikipedia at wiki.naturalphilosophy.org. But his work is absolutely amazing. He is one of those people that just cannot go into the science poetry, as we call it, and looks for real experimentation to really explain what's going on. So hats off to him. I love his work. Hopefully we'll be having him back. And if you want to help out, if you want to do some of these experiments yourself and try to push science forward, I'm sure we can do that. Let's see if we can start a group on our website so that people who are interested in doing that can do so. So let's take this session out. Remember what I always say, stay critical, stay thinking. I am Dave D. Hilster. I'm your science therapist trying to get you to the promised land of becoming a critical thinker. Ciao for now.